So looking here at a rotation practice problem for Unit 9, this is number 9.1. What we have is one of those merry-go-rounds where, you're at a park and it's a manual one, so they took them out everywhere because kids were getting hurt, but they're still super fun. And it's initially at rest. So we know it's not spinning initially, so its initial angular velocity is 0. But then a child pushes it, okay? The child grabs the bar on the outside, runs around, starts pushing it, so it has a constant angular velocity. Now, don't be confused here. While it has a constant angular velocity, we don't know what it is. But we do know that this child pushes it around for 27 seconds. That is a time. When the child stops pushing, the merry-go-round's rotating at 1.2 radians per second, which makes this a final angular velocity. What we're looking for in this problem is how many revolutions, how many complete times did the child make around the merry-go-round while he or she was pushing for it. And that means that revolutions, while it's a kind of stranger unit, it is an angular displacement. Okay, so we're looking for theta in the end here. That's what we're looking for. Now, on our new best friend, with all the equations that we have, the only equations that have theta in it are theta equals omega it plus 1/2 alpha t squared. If we wanted to find theta, we could say theta equals omega I times t plus 1/2 alpha t squared. But we run into a little bit of a problem here, because while we're looking for theta, I don't know what alpha is. And the only other equation that we have that can get us a theta is the omega f squared equals omega I squared plus 2 alpha theta. So that equation also gives us theta, but we still don't know what alpha is. We don't know what that constant angular acceleration is. So this is actually a two-stepper of a problem. What we have to do first is find this alpha. So we can use equation 2r to do that. We can say alpha equals the final angular velocity minus the initial angular velocity divided by some amount of time. We can say this then equals the 1.2 radians per second that it's going to end up with, the merry-go-round, minus the initial, which was 0, because it started at rest. So we don't even need to put it. Then we just need to divide by the time, which was 27 seconds. This will give us a quantity for alpha, which we can then throw back up. Ooh, that sounds gross. 1.2 divided by 27 gives us 0.04 repeating radians per second squared. So this value here, which we just found, while it's not our final answer, we can throw it back into this equation. So now what we can do with this is we can say, look, let's solve for theta. Theta equals the initial angular velocity times time. Well, we knew this initial velocity was 0. It started at rest. And 0 times anything is 0, so who really cares about the beginning here for this problem? So what we're left with is 0 plus 1/2 alpha, which is 0.044444, times the time of 27 seconds squared. If we run this, 27 squared, I like to do the squared first so I don't accidentally mess them up later on. 27 squared is 729 times 0.044444, just throw a few of them in. And then divide that by 2, we get a theta of 16.2 radians. That's our radian value of theta there. Now, we're not looking for radians in this problem. We're looking for complete revolutions, or just how many revolutions here. So if we want to convert from radians to revolutions, what we can recall is that 1 revolution is equivalent to 2 pi radians. And you want to be careful when you put this in the calculator, because if you just say divide by 2 pi, your calculator might accidentally be multiplying by pi instead. So when you divide by that 2 pi, it's always helpful to put those in parentheses. because we know this is about 16 divided by about 6. So our answer should be like 2 point something. If you don't get an answer that's 2 point something, you know your calculator has betrayed you. If we enter this into the calculator, 16.2 divided by the quantity of 2 pi, we get 2.58 revolutions. So the child made 2 full loops and then about 60% of another loop before they let go of this merry-go-round, and it started just traveling around at 1.2 radians per second. Okay? So this problem was a little bit more complicated than things we've seen before, simply because while we did have 3 out of the 5 things, we had to solve for that angular acceleration to use it to find that angular displacement. So kind of a two-stepper there, and then a conversion at the end makes it a little bit harder than what we've done previously, but it's still just using the equations we've been using here, equations 2r, 3r, 4r, and 5r, and working them throughout this problem. So that problem is now finished. Until next time, adios, and take it easy.